closed path. Alright, however, this equation requires a little modification, and I have written the equation on the top. Why? Consider a closed circuit path where a capacitor is being discharged. Now, there is a magnetic field around the wire. There is a magnetic field around this wire only when electric charges are flowing away from the capacitor plates. When the electric charges are not flowing, there is no magnetic field. Now remember, magnetic fields are created only when electric charges are in motion. The changing charge on the plates means that when the capacitor plate is discharged, the charge on the plates is changing. So the changing charge on the plates means that the electric field between the plates is changing. So the electric field between the plates is changing, and the magnetic field around the wires are also changing. Now Maxwell proposed that there needs to be an extra term on the right in Ampere's rule. Now the right side of the Ampere's rule is mu0 times I net, net current within the loop. Now Maxwell suggested that there needs to be an extra term there involving the changing electric field in such a situation. Now if V is the potential difference across the capacitor plates, the charge Q can be written as Q equal to CV. There's no problem there. C is the capacitance and V is the potential difference. Now, if E is the electric field between the two plates, you know that V equal to E times D. Is that right? That's the way we have been defining potential difference between the two plates, where D is the distance between the plates and E is the electric field inside the plate. Now, for a parallel plate capacitor, can you recall what's the capacitance of a parallel plate capacitor? Its capacitance is epsilon naught A over D, where of course epsilon naught is the permittivity of free space, A is the area of the capacitor plates, and D is the plate separation. And now all these things we discussed, those three equations, I have brought it back with me. And now this gives Q equal to epsilon naught A over D times ED. Q equal to CV, is that right? Where we replace C by epsilon naught A over D and V by E times D. And of course the D and D will cancel. That gives you epsilon naught AE. That is Q, that is the amount of charge on the capacitor plates. Now, if you now take the derivative of this with respect to time, we get dq by dt equal to epsilon naught A dE by dt, because as the amount of charge in the capacitor plate changes, the electric field also changes. Now, what does dq over dt represent? dq over dt represent the current in the wire. Is that right? The rate at which the charges are flowing. So, you got I equal to dq by dt, which is therefore epsilon naught A dE by dt. And this can be written as, look at the way I rewrote it. I wrote it as epsilon naught d by dt of the net flux within the capacitor plates. Why? Because area times the electric field is a measure of the total flux, isn't it? The electric field is the flux per unit area. So A times E is the net flux. So A times dE by dt is simply d phi by dt. Now, this current is not caused by the flow of charges, and Maxwell called this current the displacement current. And it is this quantity that Maxwell said should appear on the right side of that fourth equation. So this is the extra term that needs to be added to the right side of the Ampere's law involving changing electric field. Now, thus the general form of the Ampere's rule now becomes line integral B dl is, so in place of mu 0 times I net, that I net is now modified, along with this net current is the displacement current. So I net plus epsilon naught d phi by dt is now the total current. So the Ampere's rule now becomes line integral B dl is mu 0 times the total current, which is the net current in the conductor plus the displacement current. Well, therefore, let's now write down the 4 Maxwell's equations. What is the first equation, Maxwell's first equation? Well, of course, it's Gauss's law. Surface integral EdA equal to Q over epsilon naught. The net flux that is crossing any surface is the charge inside the surface divided by epsilon naught. And a similar equation for magnetic field is, if the net flux that is crossing any surface, net magnetic flux that crosses any surface is equal to 0 because it cannot enclose any magnetic monopoles. The third equation is line integral E dl is d phi by dt. And the fourth equation is line integral B dl is mu 0 times I net plus epsilon naught d phi by dt. These are the 4 Maxwell's equations. Let's now take a few minutes to talk about electromagnetic waves. Now, what do you know about electromagnetic waves? Well, everything that we do, including the video that I'm doing, is made possible because of electromagnetic waves. Light is a form of electromagnetic waves. Well, let's talk a bit about that. A changing magnetic field produces an electric field. Is that right? It is a fluctuating magnetic field that generates an electric current. So a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. I have told you this even before, that I have misspelled fields several places, so ignore that. Now, the magnetic and electric fields are perpendicular to each other. If the electric field is propagated in the horizontal direction, magnetic field will be propagated in the vertical direction. And both these fields are actually alternating. That's in the form of transverse wave. The net result of such interacting, changing fields is the propagation of orthogonal electric and magnetic fields in space. Now, what's the meaning of orthogonal electric and magnetic fields? Well, orthogonal, of course, means perpendicular. That means if the magnetic fields is propagated horizontally, the electric field is propagated vertically. These two fields are perpendicular to each other. Now, this phenomenon is referred to as electromagnetic waves. So what is the phenomenon of electromagnetic waves? Electromagnetic waves are simply propagation of electric and magnetic fields which are at right angles to each other. Now, electromagnetic waves are transverse wave whose wavelength lambda is measured from crest to crest, that is from maximum of electric or magnetic displacement. You are familiar with transverse waves. So when you talk about the maximum of the wave, it could be the maximum displacement for electric or magnetic fields. Now here I have an illustration of that. The magnetic field if this is the magnetic field, that is the electric field. So the magnetic field is the horizontal vibration and the electric field is the vertical vibration. And look at the direction of propagation. The direction of propagation is at right angles to both these. So if this is the magnetic field, suppose we call this x direction, and the electric field is in the z direction, then the direction of propagation is the y direction. Is that right? If this is x and this is z and this will be y, you can actually orient it in any way you want. The most important thing is the magnetic fields, the electric field, and the direction of propagation are mutually perpendicular to each other. I have another diagram here. Here, this is the magnetic field. The blue line, well, that is a horizontal wave, and the red wave is the electric field, which is vertical, and the direction of propagation is at right angles to both these. The magnitudes of E and B are in phase. What does that mean? The magnitudes of B and E are in phase. When the magnetic field reaches a maximum, the electric field also reaches a maximum. When the electric field is zero, the magnetic field also is zero. So the electric and magnetic fields are in phase, and look at the equation that they are related by. They are related by E equal to CB. Electric field equal to C times B, where C is the speed of electromagnetic waves in space. Where C is the speed of electromagnetic waves in free space and can be expressed in terms of, now I want you to pay attention to this and appreciate this very important and interesting concept. C is the speed of electromagnetic waves in free space. Epsilon naught is the permittivity of free space, and mu zero is the permeability of free space. You can see here electric property, magnetic property, electromagnetic property. So C is the speed of electromagnetic waves, and this speed can be expressed in terms of this epsilon naught and mu zero, like this. C equal to 1 over square root of mu zero times epsilon naught. Now, isn't that interesting? If you know the values of mu zero and epsilon naught, which you know, alright, how many of you can tell me what is mu zero? Well, mu zero is 4 pi times 10 to the negative 7. Epsilon naught is 8.85 times 10 to the negative 12. Well, all forms of electromagnetic waves travel in free space with the same speed c. Now, how many forms of electromagnetic waves do you know? Well, we've got radio waves, infrared, visible light, the lights that we see, ultraviolet, X-rays, gamma rays. They are all electromagnetic waves, and they all travel in space with the same speed c, and the value of c can be computed from the values of mu zero and epsilon naught. Replace mu zero by 4 pi times 10 to the negative 7 Tesla meter per ampere, and epsilon naught, the permittivity of free space, 8.85 times 10 to the negative 12 Coulomb squared Newton per meter squared, and that gives you c equal to 3 times 10 to the power of 8 meter per second. Now, this is an important constant, and according to Einstein, nothing can travel faster than this, right?